Urbat will be giving the next talk on high-order behavioral conformance fibrations.
Right, thank you. Hello, everyone. So there are lots of technical terms in this slide, but what this talk is really about is a categorical approach on one of the most fundamental questions in programming language theory, namely, I'm giving two programs, are they behaving in the same way? Or if they're not behaving the same, how different are they behaving? And can I quantify this kind of, and in particular, how can I prove how different they behave? So if you're an AI person, maybe how can I explain it? Yeah. So that's the subject of the talk today. And let's look at the special case of equivalence of programs. So what does it mean for two programs to behave in exactly the same way? And well, one very general and natural notion of equivalence for programs that pretty much applies to every programming language is contextual equivalence, which says two programs are equivalent if they are behaving in the same way in every context. So a context is just a program with a whole. Think of a test if you want. And being equivalent says no matter which context I put P and Q into, if one of them terminates, then the other one terminates. Yeah, so the intuition is that I can find no test that distinguishes their termination behavior. And well, as I said, this applies to pretty much every higher order language, like for example, the lambda calculus, just to give you an example. So this is equivalence, but there are many situations where we are not really interested in exact equivalence, but in how different programs are. So are they somehow a bit different or are they vastly different? This question in particular makes sense in the context of languages with quantitative features like probabilistic lambda calculi. So here's an example of a probabilistic lambda calculus. You just extend your standard syntax with a choice operator, where the intuitive semantics is you just flip a coin and then do P or Q with probability 1/2 each. Yeah? So in this calculus, a term will not converge to a single value. It will converge to a distribution of values. Yeah? So you can say I go with probability 0.3 to this value and with probability 0.7 to this value, right? And so in this setting, we can introduce what is known as a contextual pseudometric, which says the distance of P and Q is computed by just taking contexts and computing the difference in termination probability. Yeah? So here the intuition is if we think of a context as a test, if two programs are very different, then there should be some test that makes, say, P terminate with high probability and Q with low probability, so the difference should be pretty high. Yeah? And so you take the supremum over all contexts, and this gives you the contextual pseudometric. So this is a very simple natural notion, but unfortunately, it is quite hard to compute. Yeah? So let's think of an example. We take the always diverging program and here the program omega plus identity function. So intuitively, the distance should be 1/2, right? Because this always diverges and this diverges with probability 1/2. And actually, the lower bound is easy to prove because even if you put them into the empty context, there's already a difference of 0.5, right? But it might be conceivable that there is some context that produces a bigger difference. So the upper bound, that this is exactly 0.5 and not more, is not easy to prove because you would have to prove something about all contexts at the same time. So what is needed is some cleverness. And the cleverness is provided by coinductive techniques that give you efficient proof methods to prove this kind of upper bound. And there's actually a whole bunch of literature on this subject, starting by the work of Abramsky in the 1990s, who thought about the qualitative notion of contextual equivalence. And he introduced this coinductive technique of applicative bisimulations, which in connection with this Howe's method proves that applicative bisimulations are a sound proof method for contextual equivalence. And down here you see a bunch of dots. This just means that in the last 35 years, people have extended this Howe's method and the method of applicative bisimulation to many, many different kinds of languages with effects and other kinds of features. And more recently, there's this work by Courbeillet and Dalago, who extended Howe's method to applicative pseudometric, so this quantitative notion of distance of programs, and also proved this to be a sound proof method for proving upper bounds to contextual distances. So this is very nice work. So let me briefly explain how this roughly works in the setting of the probabilistic lambda calculus. So here's our probabilistic lambda calculus. We have seen the syntax, and the operational semantics is very intuitive. So it just explains for every term to which distribution of values it will converge, right? So for example, there's a rule that says if my term p goes to the value lambda x dot p1 with probability 0.3 and lambda x dot p2 with probability 0.7, and say pi of q goes to vi always, then p of q goes to this distribution, right? And if you read this, you see it's very natural. It's how you would define the operational semantics. So it's nothing surprising here. And then what Gruber and Dalago did is they introduced this notion of applicative pseudometric, which is a pseudometric on program terms. So lambda is the set of programs that is supposed to have the following property. So if you take two programs, P1 and P2, and compute their distributions of values that they converge to, then you apply each of these values to some input E, any input, and this gives you another two distributions, and then you compute the Kantorovich distance of these two distributions, right? Which is just a standard way of lifting a distance on a set to a distance on the distributions on that set. So this is a very standard way of doing this. And so this kind of non-expansivity property is what they required of an applicative pseudometric. And then the key step is to show that this pseudometric is a congruence, which just says that it's non-expansive with respect to all the operations of the language. So for example, the distance of pq and p'q should be at most the distance of the two operands. And the way how they do this is they invented a quantitative version of this Howe's method. And this version, Howe's method in general, is pretty complex. And in this case, for example, the proof uses linear programming duality. So it's really not a trivial argument. In general, my intuition why this Howe's method is often considered complex is it tries to marry a first-order notion, namely a notion of bisimulation or bisimulation metric, to a higher-order language, right? So there must be some complication there, and this is exactly the complication. So and after that, actually proving the soundness is usually easy. So that the pseudometric gives you an upper bound to the contextual pseudometric. This is easy, essentially because the contextual pseudometric is the smallest pseudometric that is a congruence and respects termination probabilities. And D is also one of these, so it must be an upper bound, right? So yeah, so this is the idea of Howe's method in the quantitative setting. So this is a quite powerful, widely applicable proof technique. But standardly, every language needs its own incarnation of Howe's method. So whenever you have a language and you change a bit in the syntax, the behavior, you need to reinvent Howe's method. You have to give new definitions, and you have to redo this often very complex soundness proof. And also, if you change the notion of conformance, so if you go from bisimulation to pseudometrics, or maybe something even more complicated, quantile valued metrics or whatever, you would also have to adapt all this, right? So wouldn't it be nice to have something like this, right? And there has been some work in this direction, starting with this Lix and POPL paper 2 years ago that I did together with a bunch of collaborators. So we introduced a kind of language-independent, syntax-free abstract approach to these coinductive techniques, which were based on algebras, coalgebras, and relation lifting, so very general categorical concepts. But they were limited to small step semantics and applicative simulations. So they didn't apply to bisimulations. They also didn't apply to pseudometrics. And this is exactly what I'm going to lift today. So today, I'm going to tell you how to do this for big step semantics, like the semantics of the probabilistic lambda calculus. And I'm also going to tell you how to extend this from applicative simulations to general conformances, which include pseudometrics, for example. And the key technique that we use is Fibrations. Yeah, so there's another talk about Fibrations today. So of course, in order to do this, we need a categorical understanding of all these terms that are displayed here in blue. So what is syntax and semantics even categorically? What is Howe's method and so on, right? So let's start with the syntax and semantics part. So here on the left, we again have our example of the probabilistic lambda calculus. So we have the terms, we have the rules. And what these rules really do is they they define an operational model, which is just a transition system on terms that says for every term which distribution of values or functions I go into, right? So D is the probability distribution or subdistribution functor because there might be some probability of non-termination. So how do we think about these structures categorically? Let's start with the syntax part. This is luckily something that Fiore et al. have been doing, have done 25 years ago. So they suggested to model syntax of languages with binders as initial algebras of binding polynomial functors on pre-sheaf categories. So in their case, they would take some binding functor on pre-sheaves over injections, and this would give you this syntax as an initial algebra. And so let's be bold, let's be courageous, forget about this pre-sheaf stuff, let's take any endo functor on any category and take its initial algebra and regard this as the abstract object of program terms. Yeah, so the mu sigma here would be the lambda in the example. What about behavior? So how do we abstract from this operational model? Well, we can observe that this expression here, the d of lambda to the lambda, is bifactorial. Namely, if we take this bifunctor here, d of y to the x, we can write this as lambda to b of lambda lambda. So, and this again explains itself how to abstract it. We just take any bifunctor whatsoever, which is contravariant in the first and covariant in the second component, corresponding to the fact that functions can be inputs and outputs of functions in higher order languages, right? And we take any what I call higher order coalgebra, which is just a morphism of this type, which is a higher order version of the usual notion of coalgebra for an endofunctor. Okay, so this gives us kind of syntax and the operational model abstractly. But what about the rules? So what do we need to model this kind of rule by what I call an abstract higher order specification? Well, what kind of structure do we need here? First of all, these rules involve terms of some kind, so certainly we would want to need something like, a free monad probably. So sigma star is the free monad generated by sigma. Think of program terms, right? More importantly, what we need is to think about unraveled behaviors, because if you look at the premise of this rule, it says you unravel the behavior of P for one step, so you tell me what P, which distribution P goes to, and then you take these PIs and also apply them, right? So you need to unravel two levels of behavior in this case. And in general, one can model this kind of structure by kind of higher order version of a co-free coalgebra, which is like a final coalgebra with parameters if you want. So think of this as the object of unraveled behaviors. And so overall, we can model rules, big step rules like this, by a dinatural transformation of this type that intuitively says, I just encode the rules into a family of maps. So I say, you give me an operation of my language, like the P of Q application. Then you tell me for each of the operands how they unravel. So for example, you unravel the P for two steps, for two layers. And then I give you the output of the rule. So in this case, the distribution that I go to. Yeah? So this is quite a pleasant abstract way of modeling operational semantics. This is kind of 50% of the contribution of this paper. But honestly, when I came up with this, I thought, yeah, this is pretty, but it must be too general to be useful, because the goal is ultimately to develop co-inductive techniques like Howe's method at this level. And amazingly, it works at this level. So not only do we get big step operational semantics abstractly, we also get a theory of applicative conformances at this level of abstraction. And so let me explain how this works. So now, for the rest of this talk, let's assume that we are given such a specification, so an abstract form of operational semantics, and we are given its operational model, so the model that it induces on the program terms. And so how do we do pseudometrics, applicative pseudometrics? We do the following. Let's, for now, assume that our language lives in the category of sets, just for simplicity, not pre-sheaves or anything. We take the category of pseudometric spaces and non-expansive maps, and we lift our behavior functor in some way to the category of pseudometrics. So, for example, if we take the behavior functor of the probabilistic lambda calculus, which was d of something, we take what is known as the Kantorowicz lifting, which is just a way of computing this Kantorowicz metric. Do we have it? Right. So we said we lift every metric to the Kantorowicz metric on distributions, right? And this is exactly what this Kantorowicz lifting does abstractly. So there is actually a categorical way of constructing these liftings from predicates, but in this setting, I don't assume any concrete construction, so it can be any lifting whatsoever. Yeah? Good. And so this is the data that we use to model pseudometrics. We take a lifting to pseudometrics. And now we can define an applicative pseudometric in this generality to be a pseudometric on the space of programs, such that the operational model, this higher order coalgebra, is non-expansive as a map from the space of programs to the space of behaviors, right? And if you go back to the probabilistic lambda calculus, this is exactly what this property here says. The non-expansivity means exactly this, right? So, but we can say this at the level of abstract higher order coalgebras. I should mention that this idea of using liftings to model applicative pseudometrics or pseudometrics in general, behavioral pseudometrics, goes back to this older work by Baldan et al. From 2014, where they did this for first order coalgebras, so standard label transition systems, but it applies very smoothly to this higher order case as well. Right, okay, so this gives us already an abstract way of talking about applicative pseudometrics, but actually, if you look at this, we didn't really use anything about the fact that this is the category of pseudometrics. We can replace it by pretty much any nice enough fibration. So we can replace pseudometrics and sets by any fibration over any category C. There will be some assumptions that I will come to later. So if you don't know what a fibration is, the general idea is it's a category that allows you to lift or pull back structure from the base category to the total category. Yeah? And this includes examples like all kinds of metric spaces with or without some axioms, all kinds of arbitrarily complicated relational structures like fuzzy relations, quantile valued relations, or structures with many relations at the same time. This is all covered by this fibrational framework. So it's a very general notion that allows you to cover many different forms of conformances like bisimulations, distances at the same time. So how does this work at this level of generality? So we have the notion of applicative conformance, parametric in the fibration, and again the lifting. And an applicative conformance is just an object in the fibration above my object of program terms, which lives down here, with the property that the operational model lifts to the fibration, so lifts from C to E. Yeah? So there is some gamma bar above this model on the object E. So for example, in the pseudometric case, this is exactly this fact that it's non-expansive, right? Okay. So again, this means that we have a nice abstract way of talking about applicative pseudometrics, bisimulations, and so on. And now, the key observation is that the congruence result, which was the key to the soundness for bisimulations and similar notions, works at this generality. So it says, roughly, if we have a nice enough fibration and a nice enough language given by this higher order specification, then the greatest applicative conformance, which is the generalization of the greatest pseudometric or the greatest bisimulation, is a congruence in the Fibrational sense. Yeah? So this is the main theoretical result of this work. Let me very briefly explain how this is proved. So, well, let me first briefly explain what nice means. So nice means that, first of all, the operational rules should respect the structure given by the fibration. So, for example, in the probabilistic case, it just means that the rules are non-expansive. So if I change the premises a bit according to the Kantorovich metric, then the conclusion should also only change a bit. Also, a nice fibration means that the fibers must carry a monoid structure that corresponds to composing relations of pseudometrics. So you need some structure like this that allows you to imitate Howe's method, because this is exactly what the proof does. It's a fibrational imitation of Howe's method. So Howe's method basically says, I take my bisimulation relation, I form its Howe's closure, which is an operation that involves composition, for example, and then I prove that the Howe's closure does it. And this turns out to be working amazingly nice at this fibrational level. And so in total, what we get is kind of a common roof over all these notions of applicative pseudometrics, plus the Howe's method. It's highly parametric, and because it's highly parametric, it applies to all kinds of languages. I walked you through this probabilistic example in this talk, but it also applies to other kinds of effects like non-deterministic, stateful. It also applies to different kinds of evaluation. So it's really a nice uniform framework to this kind of co-inductive reasoning. And what you get overall is like a method to proving upper bounds to contextual conformances. Yeah? Right, so I'm almost done. Let me just give you the big picture. So this talk is part of a research program that me and my co-authors started like 3 years ago at POPL', which we call Higher Order Mathematical Operational Semantics, which is about, say, developing operational semantics and the theory of operational reasoning at as abstractly as we can. So today I showed you how this works for Howe's method and probabilistic behavioral metrics. One thing that I also want to do and basically know how to do is logical relations, which we envision can be applied to parametricity results abstractly, because parametricity is ultimately an exercise in logical relations of a very complex form. Right, and there are other directions to go, which I will not read out. Okay, thank you.
So you mentioned the work by Kruby and Del Lago, yeah?
Yeah.
And so, I mean, it's just to be clear, like that your approach subsumes it, or can you reprove what? I mean,
yeah.
Just,
we
okay.
we cover the results.
So
yeah.
okay, because it was not. I mean, I understood that, but so my question is, you mentioned linear programming and forms of duality in their proof, and I wonder whether you have that kind of dualities in your work
yes.
too.
So that's a good question. So in their proof, it appears a bit ad hoc, yeah. And in my proof, it appears in checking this condition, this niceness condition on the fibration. And ultimately, it appears in the form where you just use Kantorovich-Wasserstein duality between the two dual presentations of the metric. This is where it's used, yeah.
Okay.
But it's used in a much more principled way.
Yes.
Yeah.
Okay.
Thanks for the talk. You had at the beginning like positives and negatives of Howe's method.
Yeah.
One thing that you didn't say that many people, some people, one might say is that Howe's method normally seems kind of magical. I mean, you pull it out of thin air and it works. After all this work, does it still seem magical or does it seem more natural?
Well, I mean, yes and no. So I think the fact that it works at this with this little structure makes it a bit less magical. But I have to admit, still, when I see it in use, I have usually very little intuition why this actually works. So when you compare it to like logical relations, which is the other de facto method to prove contextual equivalence. It is less intuitive, but I would argue that, I mean, you often get this result now for free, right? And I would argue that when it comes to actually using biosimulations, this is easier than logical relations. That's at least my view of things. So once you have this Howe's method proved, it's easy to use biosimulations. Yeah.
Thanks.
Thank you for the talk. At the beginning, you said that well, we move from contextual equivalence to applicative biosimulations to have easier proofs, and that's true for some programs, but not for all of them. Sometimes applicative bisimilarity is as hard as proving contextual equivalence, and so there is normal form bisimulation. There are normal form bisimulations that provide some easier proofs, say for fixed point operators. And I'm kind of wondering if the whole higher order abstract syntax, is it like biased towards applicative bisimulations, or do you think there would be a way to switch it for normal form bisimulations?
Yeah, that's a very good question. So it probably is even one of these bubbles. Okay, not normal form, environmental bisimulations is also a way of simplifying this method. So we haven't gone in this direction so far, so I cannot really answer whether it's biased, but we try to extend our methods to more complex, like environmental or normal form bisimulations, to simplify this method further. But right now, I cannot answer whether this works.
Let's thank the speaker.